Previous lecture, we learned about Jones vectors that were used to represent left circular polarization and right circular polarization. The important factor here would be the amplitude of the x and y component are the same, but the second element here would have an imaginary number, and for right circular polarization, then is a negative imaginary number. So for elliptical polarization, if the axis, the principal axis are on the x or the y axis, so they're symmetrical about the x and y axis, right? So here it is quite similar to the circular polarization, except that they would not have equal amplitudes. Now, the fact that they have not have equal amplitudes, we are going to represent the x component, the phase here, we can say take it to be 0. So there's a relative phase between the x and the y of pi over 2. So this one for phi y, we will give it a value of pi over 2. So if they are unequal amplitude, so we use this symbol A and B to define the unequal amplitudes, and with an additional phase, added phase for the y component. So this becomes a IB. Now exponential I pi over 2 will give you I. So this will be how it looks like if EX, that is A, is smaller than Y, or when A is larger than Y. And in this case, you will get an anti-clockwise rotation. So this would be left elliptical polarization. And for the clockwise rotation, the representation is still the same, except that we would have a negative sign for the y element part here. And again, we have similar structure here, the ellipse, but to represent the vector, then the tip of the arrow will trace out an ellipse, and it will be moving in a clockwise direction. So this will be right elliptical polarization. So they form ellipse, the tip of the arrow will trace out an ellipse which will be oriented symmetrically about the x and the y axis. And the normalized form of this would be, we will have to then have a prefactor so that a squared plus ib squared should be equals to 1. That's how we normalize it. So in that case, we would have a prefactor like this. Okay, and so from here we see that for elliptical polarized light, where the principal axis is on the x and the y axis, then you'll find that one of the element of the Jones vector is purely imaginary, and the magnitudes of the elements will not be equal. What if they are not in aligned parallel or to the x or y axis? If they are inclined at certain axis, the ellipse is inclined at certain axis, then that will be represented by, again, unequal amplitudes, but the phase difference will be at other angles. It will not be pi multiples of pi over 2, neither would it be integer multiples of pi, because that would give you linear polarization. Now let's take, for example, let's suppose that EX lead EY by an angle epsilon. So the Jones vector in that sense would be written in such a way. So again, we still suppose that phi x equals to 0. So we just have the amplitude, but phi y here would have an angle epsilon. So we insert over here. Now, in this case, we represent the amplitude here by B, which would then be written as B plus IC. And in this case, since the sign here in front of the imaginary number is positive, so we would have an anti-clockwise rotation, and that would be left elliptical polarization. Now, why we write this way? Because B exponential I epsilon, it can be written as using Euler theorem. You can then represent this by cos epsilon plus I sine epsilon. So this term here becomes B, and B sine epsilon represented by C. And the normalized form of this Jones vector would have a prefactor, because we have to make square of this and square of this equals to 1. So we divide by whatever factor that we factor out. So we will have a prefactor of 1 over root of this, so that we can make the sum of the square of the element be equal to 1. So for elliptical polarized light, where the principal axis is inclined, so it's no more vertical or horizontal, but it's inclined at a certain angle. Well, the angle is not specified here, but we'll learn about that in the next slide. Then one of the elements of the Jones vector will be a complex number. It has both real and imaginary part, and the magnitude of the elements will not be the same. This is how it looks like. And how do we calculate the angle of inclination of the ellipse, which is given by alpha, and this angle inclination is actually given by this expression here, whereby you have tangent to alpha is equals to 2 times the amplitude of x and y multiplied by the cos of that relative phase difference divided by the difference between the square of the x and y amplitude. So the ellipse will occupy a rectangle here, whereby the side will be a tangent to the surface of the ellipse, so that this rectangle will have this length of 2ex and this height here of 2ey, such that EOX will be a, E0y will be root of b squared plus c squared, and epsilon, it will be the arctangent of c over b. But when ex lacks ey, then the phase angle epsilon will be negative, and then the Jones vector will be written with a negative sign here. And this will give you clockwise rotation, and this will be right elliptical polarized light. Now, this is a sample example for elliptical polarization. Let's analyze this Jones vector. See, you have a real component for the x, and a real and an imaginary component for the second element here. So based on what we have just learned just now, so what we do is compare this to this. So we have E0x, which is a, will be equals to 3. E0y will be 2 squared plus 1 squared, and you root that, that's root 5. And the angle inclination, well, we need first to find what is epsilon, which is the arctangent of c over b. That will be 1 over 2, and that is 26.6 degree. So substituting that into the equation for the angle, you can get the value of alpha to be 35.8 degree. So the general equation for this ellipse would then be written as ex divided by 3 squared 9, ey squared divided by 5 minus, now this ratio, this value and this value, you multiply them and you take the reciprocal, multiply by 2, and then also multiply by cosine of epsilon, that will give you 0.267, and that is equals to sine epsilon squared, so that's 0.2. So this will be the equation that would represent the ellipse traced out by the vector, the resultant vector of this elliptical polarization. This is a summary of all the state of polarization that we have described before. So this is given as a reference for you, and all these are written in the normalized form: linear polarization, circular polarization, and elliptical polarization. So you will find that any Jones vector you can multiply by a real constant. So what happens is that you will be able to change the amplitude, because you're changing the prefactor only, and but not the state of polarization. For example, if you have a vector 2 and 2 here, you factor out 2, you have 1 and 1. So this would represent a linearly polarized light at an inclined angle 45 degrees with an amplitude. You change this to normalized form, then you will factor out a root 2. So the amplitude will be 2 root 2. And if you were to multiply each vector, if you multiply each vector by exponential I phi, which means you actually introduce a phase in the two elements. So phi x becomes phi x plus phi, and phi y becomes phi y plus phi. So this new vector will still represent the same polarization. Why? Because the phase difference between the two elements will still be the same. Now next, what can we do with Jones vector? Here is an example of superposing two polarized modes. Here is left and right-handed circular polarization, right? And then when you add them up, you get 2 here, and here you get 0. So the result is a linearly polarized light, which the polarized plane is horizontal. This is the x component with a amplitude twice that of each of the circularly polarized light component. And if we were to superpose a vertical and horizontal linear polarized light, superposing two of them, then look at this, it gives you the result of 1, 1 that gives you linearly polarized light. Remember, we have cross polarizer which cancels the light, but in this case, we are not talking about the polarizer. We are talking about the state of polarization. And here, important fact is that for unpolarized light, even partially polarized light, you cannot represent them using Jones vector at all. Here we are going to look into optical elements that can change the state of polarization. In fact, we are going to look into 3 selected types, 2 of which can produce polarized light, while the third one basically just modifies the state of polarization. Firstly, let's look at the linear polarizer. Now, it works because the material is able to do selective absorption, for example, dichroism. We'll learn about that in detail later. So this linear polarizer, what does it do? It will selectively remove all or most of the E vibrations in all other directions except one. So it allows only one E vibration in a particular plane. So that one that is allowed will be called the transmission axis. For example, this linear polarizer has a vertical transmission axis. So here we represent using that simplistic representation for unpolarized light, represented by 2 orthogonal components here. So when it passes the linear polarizer, this component will be totally cut off, so only the vertical component will be allowed to pass through. Okay, so we produce polarized light. Now, for a phase retarder, the second one is phase retarder. The property of the material that produces phase retardation is birefringence. So this material has actually 2 refractive indices. We'll explain in detail in another lecture. So what it does is that unpolarized light, when it enters the retardation plate, again we visualize the unpolarized light with that simplistic representation, whereby we represent it with a horizontal and a vertical component. So when it reaches the retardation plate, what it does is that it will have a fast axis and a slow axis. So this one will have a slower speed, and this one will have a higher speed. As it enters, they were in phase, but as it progressively travels into the retardation plate, it will introduce a phase difference between them, such that when they exit, there would be a cumulated amount of phase difference. So if the net phase difference that is produced is 90 degrees, that or pi over 2, then we call this a quarter wave plate. If the phase difference introduced is 180 degrees, then we call it a half wave plate. So polarized light is produced because if the phase difference is 90 degrees, we get circularly polarized light. Yeah. Now here is a rotator. If you look at this, the incident ray light here has to be polarized first. So when it enters the rotator, it will then exit with its plane of polarization rotated by an angle theta here. So this can occur because that material has got circular birefringence. So here what we have is that it modifies the state of polarization, but it did not produce polarized light. Now we will work on the mathematical representation of the polarizer, and we will represent them using Jones matrix. It is a 2 by 2 matrix with 4 elements, as you can see here, A, B, C, D, and these values here will then determine how the polarizer would modify the polarization state of the light that they are transmitting. Take example for the linear polarizer with a vertical transmission axis. So the Jones matrix, let's derive the Jones matrix that would represent this linear polarizer. So what we do is let's split it up to 2 scenarios. If we were to allow a vertically polarized light to pass through this linear polarizer, definitely we will be able to transmit that linear polarization. So we represent linear polarization as by Jones factor as 0, 1. So we should get the output as 0, 1. And we operate that matrix onto this vector. And we write out the algebraic equation that represents this. So we have A multiplied by 0, so there's nothing. So B multiplied by 1, so we have B. B will be equal to 0. And this will give us C multiplied by this, nothing. So we have D will be equals to 1. So that's what we have. But we still need to find the other 2 elements, A and C then. So for this, what we do is we allow a horizontal polarized light to pass through this linear polarizer with transmission axis vertical. Then we will get nothing. All right. So meaning that when we represent the horizontally polarized light by this vector 1, 0, what we get is nothing. So it's 0, 0. No light passes through. So then we write out the algebraic equation that represents this. We will find that A will be equal to 0 and C will be equal to 0. So therefore, we have now arrived at the matrix that will represent a linear polarizer with transmission axis vertical with element A 0, B 0, C 0, and D equals to 1. What about a linear polarizer with the transmission axis horizontal? You do the same. So operate them separately, and you find that the elements, you find that A is 1, B is 0, C is 0, D is 0. So this will represent the linear polarizer with transmission axis horizontal. Then we try one with the transmission axis inclined at 45-degree angle. So of course this doesn't represent this one. So we consider linearly polarized light entering the linear polarized in the same direction, that is inclined at 45-degree angle with x-axis, so that's 1, 1. So you should get 1, 1. If you allow another polarization, another polarized light which is perpendicular to the transmission axis of the polarizer, that would be inclined at negative 45 degrees, so that is 1 minus 1. So you will get no output, 0, 0. So from these two equation here, matrix equation, you can write out the equivalent algebraic equation, and you will find that A plus B will be equals to 1. C plus D is equals to 1. Here, A minus B equals to 0. C minus D equals to 0. So you solve this and you find that A will be equals to B. All the element has the same value, which is equals to half. So putting all this value into this matrix, then you can then represent the linear polarizer with a transmission axis inclined at 45-degree angle as bring out the common factor there. So you have 1, 1, 1, 1. This is a prefactor here, half here. So this represents linear polarizer transmission axis 45-degree angle. So in the same way, you can then make a general matrix. The previous three are special cases because we note a particular inclination already. Now, in general, if they're inclined at an angle theta, if the transmission axis is inclined at angle theta for a linear polarizer, then that matrix that represents the linear polarizer will be given by cos squared theta for A, sine theta, cos theta for B, and C is also sine theta, cos theta, and D will work out to be sine squared theta. This will be a linear polarized transmission axis at theta. You can check it out yourself. I leave it as a proof for you, give you some homework to do. Jones matrix representing the phase retarder. The required matrix must be able to transform from this phase by adding an additional phase epsilon x, and for the y component epsilon y. So basically, this is what we do. We operate the matrix, ABCD matrix, onto this so that we can get this form, whereby we have already introduced a phase over here. So in order to do that, you'll find that if you work it backwards, you'll find that this matrix will have to have this form. So A will be exponential I epsilon x, and D will be exponential I epsilon y, whereas B and C will be equal to 0. So the general form of the matrix that will represent a phase retarder would be in this form here, written here. So this will represent a phase retarder that will introduce phase of epsilon x and epsilon y. So this may take negative or positive values. Let's try it out on a quarter wave plate and a half wave plate. Now for a quarter wave plate, we would want a phase difference of pi over 2. So if we select whereby the slope axis is vertical, what we can do is the difference we know that has to be equal to pi over 2. So you will have then we will let epsilon x equals to negative pi over 4, epsilon y equals to positive pi over 4. So when this minus this, which means you add it up, is pi over 2. So you can also try other scenario. So what we have would be introducing this using that general form. We plug all this phase inside. So then we bring out this common factor. We will get a quarter wave plate with the sole axis vertical as 1, 0, 0, I. So there's an imaginary number here. And next, if the slope axis is horizontal, then you have epsilon x minus epsilon y equals to pi over 2. So epsilon x will be equal to pi over 4. Epsilon y, we take it to be negative pi over 4, writing this way. Then in the case when you take this factor out, you'll find that this will work out to be negative I. So this represents quarter wave plate, so axis horizontal. So next we try on a half wave plate. Then you know the phase difference must be equals to pi. Doing the same, for a slope axis vertical, you can then write it this way. So we let epsilon x is negative pi over 2, epsilon y as pi over 2. So bring out this factor, we will have this one here. And then for the half wave plate where slope axis horizontal, it will work out to be putting this here and this here, it will work out to be in this form. Now note here that these two matrices are the same, right? Except the prefactor here. The difference only is in the prefactor, right? So why are these two matrices the same? Because advancing the phase by a pi is physically equivalent to retarding the phase by pi. That's why you have the same matrix to represent halfway plate end for slow axis vertical and horizontal. We are up to the final part of Jones matrix for we'll derive this for rotator. Remember, rotators are able to modify the state of polarization, but it will not produce polarized light. So for a rotator that produces rotation of angle beta, then it's required that if a linear polarized light, the plane of polarization is inclined at angle theta, passes through the rotator, when it exits, it would have rotated such that, and the orientation of that plane polarized light would be at an angle theta plus beta. That's what we want. So in other words, we have a linearly polarized light inclined angle theta represented by Jones vector cosine theta sine theta, and that should give us a resultant linear polarized light with an angle of inclination theta plus beta, and over here cos of this and sine of this. So we need to find elements for the Jones matrix that represents the rotator. So it's for the rotator. So if you write the algebraic equation to represent this, then we have A cos theta plus B sine theta equals to cos theta plus beta. Write it the other one, C cos theta D sine theta will be equals to sine theta plus beta. We use the trigonometric identity, which gives us the sum of two angles. The cosine of the sum of two angles will give you cos theta cos beta minus sine theta sine beta. And over here, sine of the sum of two angles will be sine theta cos beta plus cos theta sine beta. So comparing this equation, these terms here with these terms on the left hand side here, so you'll find that A will be equals to cos beta, and here B will be equals to negative sine beta. C would then be equals to sine beta. D would then be equals to cos beta. So therefore, the matrix that would represent the rotator that will introduce a rotation of angle beta will be written as cosine beta, negative sine beta for B, sine beta for C, and cos beta for element D. So this is just a summary of the Jones matrices that represents linear polarizer, phase retarder, as well as rotator. So for your easy reference. Now, what are the uses of this polarizer? Well, we have already discussed about this in a previous lecture of how to produce circularly polarized light by using a linear polarizer. So you create a linear polarization from unpolarized light at an angle inclined at 45, which you can resolve to a vertical and a horizontal component of equal amplitude. And then you let it pass through a quarter wave plate that will introduce a phase difference between the two components. So when they exit and superpose, you get a circularly polarized light. So that's the how it works. So now what we do is we're going to use Jones calculus. So we are going to operate the matrix that represents the quarter wave plate with slow axis horizontal, which is written in this form. And we operate that on a linearly polarized light at 45-degree angle, written in this form, which is the normalized form. And if you multiply out, you have a exponential I pi over 4 divided by root 2. That will be the prefactor. So this times this is 1. So you have 1 here. This times is 0. This times this, you got negative I. So just looking at what's in the bracket here, that would tell you that it's a right-handed circular polarized light. If the quarter wave plate has got a slow axis which is vertical, therefore this will be written with a positive I here. And when you operate that onto the same linearly polarized light at inclined angle 45 degree, you will then work out to have a circularly polarized light, which is left circular polarized. This is positive sign here. Now, this is another example of a problem. So now what happens when we allow a left circular polarized light to pass through not a quarter wave, not a half wave, but an 8-wave plate? That means it will introduce, there would be a phase difference between the two by pi over 4. So there's a phase retarder of pi over 4. So this time we try out like, let's write epsilon x equals to 0. So we introduce a pi over 4 at epsilon y. So then we write the matrix in this form. Remember I told you that we can actually write in different forms as long as the phase difference is what is stated. Then we allow this to operate on the left circular polarized light. So what do we get? 1 times 1, 0, still 1, 0 and 1, 0. Then this element in this vector will be I, exponential I pi over 4, and is equal to exponential I 3 pi over 4. So the resultant Jones vector shows that the light would be elliptically polarized and the components are out of phase by 3 pi over 4. So expanding this one using Euler's expression, you will have cos 3 pi over 4 plus I sine 3 pi over 4, which gives you negative 1 over root 2 plus I 1 over root 2. That will be the element for B plus I C, right? So the resultant Jones vector is written in this form. So compared to the standard notation that we have defined earlier, so our A would be 1, B is negative 1 over root 2, and C would be 1 over root 2. From there, we will have it would result, since A and C have the same sign, then what we have would be a left elliptical polarization. And here, EOX equals to 1, EOY is root of square of this half, add up 1. So that's 1. And then, so EOY is 1, this is 1 also. And alpha would work out to be negative 45, substitute that in. Okay, so then here is an important note here. So if the polarized light, which we represent by Jones vector, passes sequentially through M series of polarizing elements, which are represented by M1, M2, M3, M until MM, the mth component, such that when you operate the matrices onto the Jones vector, you will get a resultant polarization of light. But so we can actually represent all this by an overall system matrix, MS here. And note that the sequence is important now. This one is written from the output back to where the first polarizing element that polarized passes through. All right, so from this lecture, you should be able to do all this. After you've gone through, you should be able to apply Jones vector to describe elliptical polarization. And you should be able to derive Jones matrices to represent linear polarizer, retarder, phase retarder, as well as the rotator. And you should be able to use Jones vectors and matrices in different optical systems to find out what would be the output light, what kind of polarization would result. Yeah, thank you.